So yeah, let's get started. So hello everyone, I am Himanshu Mishra and I am a PhD research scholar in Applied Mechanics Department, IIT Madras, and I am your TA for this course Heat Transfer NPTEL. So here I will be doing the live interaction every week uh, for the for this course. I mean for the topics that has been covered previous week. So today I will be doing a live interaction. I mean discussing the questions and some concepts of heat transfer that you have been already covered this week in the NPTEL course. So yeah. So if you have any doubts or any problem while I am discussing, you can just ask me in between the doubt clearing sessions. So we will start with the first basic concepts, which is define the modes of heat transfer. So as we know that heat transfer is just transfer of thermal energy from the higher temperature to the lower temperature, and this can be done by the three modes. Okay, so this can be done by the three modes. So the first mode is let's say conduction. So I will be just revising whatever you have seen in the NPTEL videos. So in the conduction, there will be the transfer of the energy through the vibration of the lattice atoms or the exchange of the electrons in the solid body. So the conduction can take place in both in solid body as well as liquid and gases. So for solid, it is due to the vibration of atoms in the lattice, or if we consider the good conductor of metal, it can happen due to the free migration of electron also. Whereas in liquid and gases, the conduction can take place, particularly if the liquid or any fluid is in a stationary state. In that case, the heat transfer can occur due to the diffusion process or the collision of the atoms. So for the gases, we know that there are many atoms that is homogeneously distributed inside the phase, and when these atoms collide with each other, it actually transfer the energy from the higher energy atomic atom to the lower energy atomic state. Similarly, in the liquid where the atoms are closely packed with each other, there will be transfer of energy due to the collision. So in fluid, the conduction can happen due to the collision or the diffusion process. So the experiments reveal that in a conduction heat transfer, the heat transfer actually proportional to the temperature gradient as well as the thermal conductivity, which is a material property. So from the Fourier's law, we know that we can express the heat transfer via conduction by Q Ka uh, dt by dx. So here K is my thermal conductivity, which is the material property. A is the cross section area, and dT by dou is the temperature gradient. So the heat transfer in the conduction depends on the temperature gradient. So this is my Fourier's law. Similarly, there is other mode of heat transfer like convection. So in convection, the heat transfer take place due to the bulk motion of the fluid. So in the conduction, it is due to the diffusion process, whereas in convection, there will be the diffusion as well as the bulk motion of the fluid parcel. So for example, I have a flow inside a channel, and there is a some large size fluid parcel that that is carried away due to the fluid motion, due to due to some fluid motion that in a specific direction. So this fluid, due to the motion of this fluid parcel, uh, there will be the transfer of thermal energy from the higher temperature to the lower temperature, which is called the convection heat transfer. So this happened due to the bulk motion of fluid as well as from the diffusion of particles. Similar, so this convection heat transfer can be defined by the Newton's law of cooling. Just like a Fourier's law, this Newton's law of cooling is obtained not from the first principle or not from any mathematical exercise. It is derived from the experiments, which can be written as. So here H is my heat transfer coefficient and A is my surface cross-sectional area. So unlike the conduction, here the heat transfer actually depends on the temperature difference, whereas in conduction the heat transfer depends on the temperature gradient. Similarly, we can define the third mode of heat transfer, which is the radiation. So we know that in radiation there is a transfer of thermal heat transfer due to the thermal radiation. So any body having a non-zero temperature can able to emit the thermal radiation, and these thermal radiation transfer from the higher temperature to the lower temperature. So the in case of the radiation, this thermal radiation heat transfer can take place in vacuum, and this heat transfer can be governed by the Stefan-Boltzmann law, which is given by where sigma is my Stefan-Boltzmann constant. So here we revise three modes of heat transfer, which is conduction, convection, radiation. There are various examples where these three modes can together present in the heat transfer problem. It is not necessary that only one of these mode can be responsible for the heat transfer. So let's define the thermal diffusivity. So in the conduction problem, the thermal diffusivity can be defined as it is the ratio of heat conducted to the heat storage. So if you consider any body, let's say there is a sphere here, I some sphere. So in the sphere, it can store heat as well as it can conduct the heat. So the conduction of heat governed by the Fourier's law, but the storage of the heat actually explained through its material property. For example, the heat storage can be defined as the amount of heat it can absorb to increase the temperature by 1 degree Celsius. Whereas there is a property which we already discussed is the heat transfer or the heat conduction due to the Fourier's law. So this thermal diffusivity actually tells us that how much heat is conducted as compared to the heat is storage. So for example, if my thermal diffusivity is greater than 1, it says that the heat, whatever heat you supply to this object, the heat, it will transfer the heat more as compared to its storage of heat. So here the more there will be more heat transfer if the diffusivity is greater than 1. Similarly, if diffusivity is less than 1, then whatever amount of heat you supply to the object, it will store more heat compared to the transfer of the heat by the conduction. So this so the heat conduction can be defined by the thermal conductivity. That means if I have a more thermal if any material have more magnitude of thermal conductivity, it will transfer more heat. And similarly, the storage of heat can be defined by the density and the heat capacity of the body. So any doubt until this?
No, sir.
Yeah. Okay. So let us come to the third problem. So in this problem, consider a plain rectangular wall of length L and breadth V, thickness W. Now if one side of the wall along the x direction is maintained at the constant temperature Ts, and the other side of the wall is subjected to a constant heat flux, then select the correct boundary condition of the system. So let's say we have a wall. Let define here x equal to 0 and here x equals L. So the question says that if at the left side I have a fixed temperature which is defined as Ts, whereas at the right side of the wall uh, we are imparting the constant heat flux, which is let's say Q double dash. So what should be the boundary condition? So from the left hand side we know that we can define the fixed temperature. So the boundary condition is just a straightforward, which is T at x equal to 0 will be Ts, whereas at the right hand side we have a constant heat flux. So we can define the boundary condition like constant heat flux x equal to L, and the this heat flux can be given by the Fourier's law, which can be dou T by dou x. So from the options we can see that the option C will be the correct answer, because the temperature Ts is given only on the left hand side. It will not be transferred completely at the right hand side, because the heat transfer will, due to the heat transfer there will be some decrement in the temperature along the wall. So this we can reject the B option as well as the D option. And according to the A option, the temperature at the left hand side will be 0, which is not true. So the option C will be the correct answer here. So next we describe the remaining boundary condition through the conduction process. So in the above question we describe the constant temperature boundary condition and the constant heat flux boundary condition. There are other boundary condition which are which can be present in the problem and which can be helpful to solve the conduction heat problems. So just for sake of completeness, I will the writing the constant temperature boundary condition, where you specify the temperature at particular location as we did in the previous question. Then there is a constant heat flux condition. In the constant heat flux condition, like the previous question, there is a heat flux at some particular location of the problem. So let the location be x equal to x, and the heat flux can be defined from the Fourier's law. Similarly, there can be the boundary condition like the insulated boundary condition. So in the insulated boundary, the heat flux will be zero. There will be no exchange of heat through the insulated boundary. So we can define from the heat flux case, we can define the Q heat flux will be zero, which is dou T by dou X, which give us dou T by dou X equal to zero. So this will be my insulated boundary condition at some specific location of the problem in the problem. Similarly, there might be the cases when there is the conduction and convection present together can present inside the problem. For example, let's say I have a slab. I can define the temperature here, T1 and T2, and there is a flow along with the slab, and here the temperature is T infinity. So here there will be two modes of heat transfer. First, in slab it is due to the conduction, which is governed by the Fourier's law, and in the fluid it is due to the convection, which is governed by the Newton's law. So, however, the heat transfer will be the same in both mode of the conduction. So we can define as let's say I have defined this region as 1 and 2. So the heat transfer in 1 will be equal to heat transfer in the 2. So I can define as in region 1 the heat transfer is due to the conduction, which is T1 minus T2. Let's say I define here distance L equals to, in the second region the heat transfer is due to the Newton's law, which is Hs minus T infinity. So this is one of the boundary condition which requires when there is a multiple modes of heat transfer present in the system. Similarly, let's say I have a radiation heat transfer instead of this convection. Let's say I have a same wall with same specification, and there is a radiation in region 2. So radiation heat transfer will be dominated if the temperature at the right side of the wall will be higher. So in that case you cannot neglect the radiation heat transfer. So let's say if my T1 is 2500 degrees Celsius and T2 is 2000 degrees Celsius, you can see the T2 is still higher, and hence in this case we should consider the radiation heat transfer at the second region. So similarly, in the first case we have defined here, we can define this combination like and in the second region the heat transfer will be due to the Stephen-Boltzmann law. The T infinity is some temperature present outside the far away from the slab. So these are my boundary condition when the multiple heat transfer may present. Now there is one other boundary condition that may require, and it is let's say you have there are two slabs which is present, slab 1 and slab 2, and the contact between these two slabs is very rough. In this case we need to define the boundary condition between this at the contact between the two slabs. So this can be done in two ways. The first phase, as there is a temperature difference, let's say T1. So the heat transfer is governed by the Fourier's law. We already know this, and the heat transfer is proportional to the dou T by dou X. That means there is a slope which is defined here. So this slope is according to the Fourier's law is directly proportional to the heat transfer. So one requirement is that the temperature at just left side of this first slab, it should be equal to the temperature is just right side of the second slab. So for example, here my temperature should be T2, and here just right side my temperature should be T2. I'm talking about this region. So this is my first slab and this is my second slab. So at the interface, my temperature should be equal, which is T2. The second boundary condition we can define as the equality of the heat transfer. Just like in the previous case, I have defined like this and this. My heat transfer in the first slab equal to the second slab, and in both slab, uh, the heat transfer will be governed by the Fourier's law, which is Ka dou T by dou x Kb. So these are some of the boundary conditions that you may require to solve the differential equation, conduction differential equation. So any doubt in this?
No, sir.
No.
Okay. So okay, then let's move to the other problem. So in this problem, the I have shown the conical section, and there are two sides of the conical section, x2 and x1, and the temperature T2 and T1 respectively at each sides of the conical section, and we have to define the relation of the temperature and the heat transfer here. So we have given the relation of the diameter, which is Ax. A is some constant. So in this slab, the heat transfer will be governed by the Fourier's law. So let's write that first. Okay, where my area can be defined by pi by d square, which is pi by x square. So when I substitute this area into this equation, it will be pi by 4 a square x square dt by dx. So I can define this like q dx x square 4 by pi a square and k and dt. So this is my equation 1. So now I need to integrate this equation. So what I have done is, I have a slab, conical slab, let's say this. So from x1 there will be some heat transfer. So I define some small element here, and I am integrating as I am moving towards T2 or towards x2. I am integrating, so I will get some relation of temperature in terms of x here. So let's integrate it. Let's integrate from x1 to some x, and the temperature of this element will be T. So on integration we will get 1 minus x so it will be x1 minus t minus t1. So I can define my temperature at some location x, some arbitrary location x, as 4q by pi k square 1 minus x plus 1 plus x1 plus t1. So this is my relation of temperature T at x location. So now if I want to define the heat transfer, I don't know anything about Q. What is the heat transfer from x1 to x2? So the heat transfer will be something like this. So there will be some profile from x1 to x2, and I, as of now, I am defining some temperature at some random location x. So to define the total heat transfer inside this body, I need to substitute the temperature T2 in place of T and x2 in place of x. So I can substitute here as T2 4q. Here I will substitute x2 plus x1 and plus t1. So this become t2 minus t1 pi by 4 k square. And let's define this quantity as x bar. So x bar q. So my heat transfer will be pi by 4 k a square t2 minus t1 and x bar. So this will be my heat transfer, and this will be my temperature distribution here. So any doubt in this?
No, sir.
Okay. So let's move to the other problem. So in this problem, I'm showing the one slab, and there is a heat transfer in the first region due to the convection, and this is the heat transfer due to the conduction, and here the heat transfer is again due to the convection. So we have to determine the heat steady rate heat transfer to this glass window and the temperature of its inner surface for the day during which the room is maintained at 20 degrees Celsius, while the temperature of the outdoor is minus 10 degrees Celsius. Okay, so we have given the heat transfer coefficient at region 1 and at region 3, and the thermal conductivity that can be used at region 2. So we need to find this temperature T1 and T2 here. Okay, so we know that the resistance can be defined as inversely proportional to the conduction or the heat transfer coefficient. So the resistance for the first case will be 1 by H1A for R3 is actually 1 by H3A, and for the second region it will be L by KA. So A is my cross section area, which will be same for the all cases, and I can since these resistance are in the series arrangement, so I can just simply add all this resistance to find the total resistance of the problem. So for this, my total resistance would be just addition of all the resistance. So this will be my total resistance, and the heat transfer can be defined from the let's say T infinity to T infinity 2 and my total resistance here. So my value of the total resistance will be 1.5 10. My thickness will be given as 8 mm, which is, and the thermal conductivity of this second region or the slab can be 0.78, and H2 will be point. So yeah, so on solving this equation, we will get the heat transfer as let me check, as something about 266 watt. Now we need to define the temperature T1 and T2. So we need to incorporate the how the heat transfer is taking place at T1 and T2. So in the first region, it will be the heat transfer will take place due to the convection. So we use the Newton's law. So it will be from 20 degrees Celsius. So the temperature will change from the 20 degrees Celsius to some T1 due to the convection here. So let's say Q is equal to HA T infinity 1 and T1. So we know the Q, which is 266 watt, and we know the H and area, and we can obtain T1 from this relation, which is 10 0.1.5 20 minus T1. Similarly, for the T2, we can have a multiple approach. We can like we have defined the convection heat transfer from 20 to T1. We can define the convection heat transfer from T2 to minus 10 by the Newton's law of cooling. So we can get temperature T2 by the Newton's law of cooling, where the temperature vary from T2 to minus 10. The other way is we use the Fourier conduction heat transfer, where the temperature is changed from the T1 and T2. So we already get the temperature T1 from this relation. If you solve this relation, we will get temperature T1. And now the temperature T1 is a known quantity. We can either use Fourier's law to find the T2 when we consider the heat transfer in the second region, or we can use the Newton's law of cooling, where the temperature T2 changes to minus 10 degrees Celsius. So the one way is to define, by the way, the heat transfer will be same in all the three regions. So it will be just Q H3A minus 10, sorry, T2 minus 10. We can define like this, or K, KA T1 minus T2 and L, which is K is 0.78. Multiply T1, which is the known quantity, and T2 it is to be find out, and L is my 10 to the power minus 3. So we can get the T2 relation from here or here, and T1 relation from here. and we already obtained the heat transfer from the resistance formula. So, any doubt on this?
No, sir.
Okay. So let's further go into the same problem. So in the above problem, we saw that there is one slab and there is a convection heat transfer at the both side of the slab. Now, if we let's say have a multiple slab and there will be the convection at the left side of this region 1, left side of the slab, which is region 1. This is region 2 and this is region 3 and this is region 4. So there will be the convection at region 1 and region 4, and conduction at region 3 and region 2 and region 3. So let's define the temperature, T infinity 1 here, let's say T1, T2, T3, and here T infinity 4. So just like before, we need to write the resistance function uh, for this system to simplify the problem. So it is always beneficial to write the resistance functions first before solving the heat transfer problem. So my resistance function for the region 1 will be H1A. For region 2, region 4, it will be H4A, because it is due to the convection. And for the region 2, it will be L2, K2, and this will be K3, V3. So in this way you can just simply keep adding slabs, not necessarily in a series manner, but also you can add slab in the parallel manner, and you can define the uh, other mode of heat transfer like convection radiation at the uh, end of the slabs, and in this way you can keep adding the resistance functions. So for the series connection, we just need to add the resistance all, do the summation of the all resistance R2, R3 and R4. Now if we have, let's say, the parallel connection, or let's say I have defined slab uh, like this, and my heat transfer is going toward the right direction. So if I define my slab in a parallel mode, then I can define my total resistance as R1 plus 1 by R1 plus 1 by R2. So the total heat transfer will be just the temperature difference and the total resistance function. Yeah. Any doubt?
No, sir.
Okay. Okay then. Let's move to the some basic problem. So this is a true or false problem. So if any of this statement is true, we have a correct answer, as we can choose option A as a correct answer, or if any one of this option become false, we will choose the option B as a correct option. So we have given the two statement. The first statement tells us that the steady state for a given heat transfer system implies that the temperature can be a function of position, but at a given position the temperature is not a function of time. So the conduction heat transfer can be governed by the differential equation, which is dou T dou square, dou T by dou y square, some heat generation, and some change in temperature. So the first statement says that for the steady state, the heat transfer will be function of space only and not time. So in the steady state, the RHS will be 0, and we will get only the Laplacian of the temperature and the heat generation, which is equal to 0. And this equation, this partial differential equation, will be the function of space only. So my first statement will be correct. The second statement tells us that the Newton's law of cooling is a fundamental relation in the convective heat transfer, which cannot be derived but is a result of large number of experimental observation. So this I already explained in the first question, where the Fourier's law and the Newton's law are actually come from the experiments and not from any mathematical derivation. So both statements are correct. So here my correct option is true. So let's go to the other true and false question. So here the heat flux in a given direction is no longer strictly parallel to the temperature gradient in that direction for the anisotropic material. Simply put, if there is no temperature gradient in the YZ direction, there may still be heat flux in that direction. So basically from the above equation we can see that the temperature gradient does not necessarily be there in some specific direction. So in all the above problem that we have solved, we have considered a basic assumption that my material is homogeneous. So there will be temperature gradient in only in the x direction. But for the anisotropic particle, this is not true, because in anisotropic particle, the property of the material can be different in the other direction. So in the anisotropic particle, my Ka would not, Kx would not be equal to the Ky, whereas Kx is the thermal conductivity in the x direction and Ky is the thermal conductivity in the y direction. So yeah, the second statement says that there are many materials where the variation of a transport property with the direction is an important aspect of the material behavior. Example of this common isotropic. Yeah, so second statement is true. So generally the material whose structure contains a lot of fibers. In those structure, the material properties like thermal conductivity vary in each direction. Like in the x direction, my thermal conductivity will be different from the y direction. So again, the option will be the true here, because second statement is correct. So yeah, any doubt until now?
No.
Okay, so this is the last question now. So the question says that the electric resistance heater is embedded in a long cylinder of diameter 30 mm. When the water with a temperature of 25 degrees Celsius and the velocity of 1 meter per second flows crosswise over the cylinder, the power per unit length required to maintain the surface at a uniform temperature of 90 degrees Celsius is 28. When air also at 25 degrees Celsius but with a velocity of 10 meters per second is flowing, the power per unit length required to maintain the same surface temperature is 400 watt per meter. So calculate and compare the convection coefficient. So in this question we have two situations. For example, let's say in the first situation the water is flowing and the temperature at the surface is 90 degrees Celsius everywhere, and the temperature of the water is given as the 25 degrees Celsius. So this is my case A. In the case B, air is flowing and the temperature is still same 90 degrees Celsius at the surface, and the temperature of air is given as 25 degrees Celsius. This is the case B. So the heat transfer per unit length for the case A is given as 28 10 to the power 3 watt per meter, and for the case B it is given as 400 watt per meter. So we need to calculate the convection coefficient. So there will be the heat transfer due to the convection. So heat will be transferred from the solid body to the fluid, and and this can be written as via Newton's law, HA T surface and T fluid. So Tf is my temperature of fluid and Ts is the surface temperature. So we need to find the heat transfer coefficient, HA. So here I can define Q pi d 90 minus 25 as HA by the diameter is 30 mm, 90 minus 25. So it will be, let's check, around 4570. So this will be the value we will get if we calculate this. Similarly, for the case B, I can write from the same expression 400. This is my heat transfer in case B, pi d. I can directly substitute. So this will be 30, 90 minus 25. So in this case, my heat transfer coefficient will be 65 Kelvin, or the Celsius. We have considered the Celsius. So we can see that the heat transfer coefficient in case A is greater than in case B. So even the water is flowing with the velocity of 1 meter per second and air is flowing with the velocity of 10 meter per second, we found that the heat transfer coefficient in the first water case will be higher than when we compare with the air case. So there will be more heat transfer in the water case compared to the air case. Even the velocity of the water is much 10 times lesser than the velocity of the air. So we can conclude that this heat transfer coefficient not only depends only on the velocity, it depends on the property of the fluid and the geometry of the particle and many other things also. So just on the basis of the velocity, we cannot just conclude that if my velocity of the fluid is higher, the heat transfer will be more. There are many other factors where this heat transfer coefficient will be depend on, and the only way to define the accurate uh, define the heat transfer coefficient accurately is to know the heat transfer Q and then use the Newton's law of cooling. So yeah, any doubt? Any doubt? I mean, in the whole session we have discovered, or anything from the previous week of the NPTEL videos?
No, sir.
Okay. Okay, then. So this week I have discussed about the mainly the conduction in the plane slab and the mode of heat transfer and the boundary condition. In the next week, I will discuss about the conduction in the radial geometry or the radial coordinate system or spherical coordinate system and the critical thickness of insulation and whatever the topics that are covered in the next week. So yeah, so that's it for today. If you have any doubts, you can tell me now, or you can just write in the NPTEL. You can drop any doubt in the NPTEL course.
So this PDF is available on the site.
Um, yeah, I mean, I will upload the PDF. Let's see the NPTEL share this PDF with you guys. I cannot say clearly if this PDF. I mean, if you recall, you can contact me. I will send you this PDF. I mean,
Okay.
Anything to ask? Yeah, that's it for today. I mean, you can leave.
Thank you, sir.
So Pujari, we have concluded this lecture for today. We have done for today. So let's meet next week.
Yes.